Dear students, in this session, we will do some problems on Thevenin's and Norton's theorem. First, using Thevenin's theorem, find the current through 6 ohm resistor in the following network and find the voltage across the load. This is the given network. To find the Thevenin equivalent of a given network, first consider the given network. Step first, this is the given network. Step 2, to find the Thevenin's voltage VTH. We know, to find the Thevenin's voltage VTH, remove the load resistance by open circuit in which the current is to be found and find the open circuit voltage, that means VO, which appears across the two terminals A and B, where resistance has to be removed. Therefore, VO equals I into R2. VO equals VO across the terminals A and B. VO equals I into R2. That means the current I is flowing in this mesh, I into R2. So as the load is open, there is no potential difference. There is no potential drop across R3. Therefore, the potential difference between the two terminals A and B is same as that between X and Y. This voltage is called Thevenin's voltage. That means VTH. Therefore, VO equals, that means we know in the mesh the current I, first I must be found. I equals E, that means voltage, divided by total resistance in this mesh, that means R1 plus R2. Therefore, V0 equals, VO equals I, that means E divided by R1 plus R2 into R2. That's equals, the voltage source E equals 10 volts. Therefore, 10 divided by 10 plus 2, that means R1 equals to 10 ohm, R2 equals 2 ohm into 10, R2 equals 2. That's equals 20 divided by 12. 4 3s are 4 5s are 20. Therefore, 5 divided by 3. That's equals 1.66 volts. That's equals VTH. This is the Thevenin's voltage. Next, we must find the step 3. We must find the Thevenin's resistance RTH. To find the Thevenin's resistance, by looking back from the load terminals in the network, by replacing the voltage source by short circuit and by their internal resistance and current source by open circuit, this circuit extended by like this look like this. Therefore, RTH equals R1 parallel R2. These two are connected in series, that means plus R3. Therefore, R1 equals to 10 parallel 2 plus 4, that's equals 10 into 2 divided by 10 plus 2 plus 4, that's equals 20 divided by 12 plus 4. So 4 5 is 4 3 is that's equals 5 plus 12 by 3, that's equals 17 by 3, that's equals 5.66 ohm. Next, step 4. Step 4. Replace the entire network by simple Thevenin source of voltage VTH. You know the VTH value 1.66 volts and Thevenin's resistance RTH, that's equals 5.66 ohm. This is connected in series with it. Next, step 5. Step 5. Finally, by connecting the load resistance across the terminals A and B and calculate the current or voltage across A and B, I mean the load. Therefore, the current flowing is IL. You know the IL equals VTH divided by RTH plus RL, that means total resistance. You know the value of VTH. VTH equals 1.66. VTH equals 1.66 volts divided by, you know the value of RTH equals to 5.66 ohm plus, you know the load resistance is equals to 6 ohm, that's equals 1.66 divided by 11.66, that's equals 0.14 amp. And also we must calculate the voltage across the A and B, that means VAB equals, you know the value of IL equals to 0.14 amp, 0.14 into 6, that's equals 0.84 volts. Next, next problem, using Norton's theorem, calculate the current flowing through the 10 ohm resistance. You know, to find the Norton's equivalent of a given network, first consider the given network. Step 2, to find the ISC or IN, that means Norton's equivalent, I mean Norton's current. So the current I is flowing in this mesh means I equals E divided by effective resistance or EFF. First we must find the effective resistance. So REFF equals R2 parallel R3 plus R1. First we must find the I equals to, I mean the current I is flowing in this mesh, I equals E divided by effective resistance. Effective resistance equals to R2 parallel R3 plus R1. That's equals 6 into 4 divided by 6 plus 4 plus 2, that's equals 24 divided by 10 plus 2, that's equals 24 plus 20 divided by 10 equals 44 by 10, that's equals 4.4 ohm. Therefore, I equals, the E voltage equals 10 divided by, the effective resistance, that's equals 4.4 ohm. So, 2.27 amp. I equals 2.27 amp. And finally, we must calculate the value of ISC. ISC or IN, Norton's current, ISC or IN. IN equals I divided by R2 plus R3 into R2. The ISC equals I divided by R2 plus R3 into R2. So, that's equals 2.27 divided by 6 plus 4 into 6, that's equals 0.227 into 6, that's equals 1.36 amp. So, Norton's current equals to 1.36 amp. Next, we must find the Norton's equivalent to Norton's resistance. This circuit is written by like this. It's look like this. Therefore, Norton's resistance Rn equals to R1 parallel R2 plus R3. These two are connected in series with the R3. Therefore, 2 into 6 divided by 2 plus 6 plus 4, that's equals 12 divided by 8 plus 4, that's equals 12 plus 32 divided by 8, that's equals 44 divided by 8, that's equals 5.5 ohm. Next, step 4. Step 4. Replace the given network by a simple circuit containing a current source of current ISC and or IN, Norton's current, or IN, and looking back resistance RTH, that means Norton's resistance, is connected in parallel with it. So, IL, the current value of IL, load current IL equals ISC into RN divided by RN plus RL. So, therefore, 1.36 divided by 5.5 plus 10 into 5.5, that's equals 1.36 divided by 15.5 into 5.5, that's equals 0.087 into 5.5, that's equals 0.4785 amp. Like this, we can calculate the current flowing through the 10 ohm resistance. Thank you.